Okay guys, this was part 2 of the acid and base lecture 2 videos, and we're going to look at the relationship between Ka and Kb that we learned about in the first part of this lecture, and then look at how those relationships can be used to do some calculations. So a relationship exists between Ka and Kb values when we're looking at conjugate acid-base pairs. So what do we mean by a conjugate acid-base pair? So previously we learned that if we had something like NH3, which is an acid, it's a weak acid, but it is an acid, when it gives up or donates its hydrogen, it becomes NH3, which is its conjugate base. So we would say NH4 and NH3 are a conjugate acid-base pair. All right, so what we're looking at here is the Kb value for the conjugate base. So if we take NH3, add it to water, we produce NH4 and OH. That's the basic reaction here. The Kb value here is 1.8 times 10 to the negative fifth. And the expression for that would be the concentration of my products, which would be NH4 and OH over the concentration of my reactants, which would just be NH3 because, again, we would leave water out since it's a liquid. Then for the acidic reaction here, we would take our acid plus water. It produces NH3 plus the hydronium ion, or H plus. The Ka value for that reaction would be 5.6 times 10 to the negative 10th. And again, our expression for that would be the concentration of our products, which would be NH3 and the hydronium ion, divided by the concentration of my reactants, which would be NH4. So those two, again, there's a relationship between those. And what we see is if we take the expression for my Ka value, which is this one here, and we take the expression for the Kb value, which is this one here, and there's some things there that can be canceled out. NH4 is on the top and on the bottom, NH3 is on the top and the bottom, and so those can cancel out. And we end up with the concentration of OH minus times the concentration of H3O plus, or hydronium ion, and that we know already is equal to Kw, which we saw in the very first lecture on acids and bases. And so this relationship gives us several mathematical relationships that we can use in our calculations. And so we know here the Kw here is equal to Ka times Kb. And so if we take the negative log of both sides of that equation, we end up with pKw is equal to pKa plus pKb, which would be equal to 14 at 25 degrees Celsius. We know the pKw is 14 at 25 degrees Celsius. That was a constant. And then we also know Kw is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. And again, if we take that equation and take the negative log of both sides of that equation, we end up with pK is equal to pH plus pOH, which again is constant at 25 degrees Celsius and equal to 14. So all of these equations, equation 1, 2, and 3, are all true equations, but keep in mind that equation 2 and 3 are only true at 25 degrees Celsius. At higher temperatures, or at lower temperatures, either one. At higher temperatures, the sum in either case here, equation 2 or equation 3, is going to be less than 14 at higher temperatures. And so if you think about it, Kw is temperature dependent, we know that, and the autodissociation of water is an endothermic process. In other words, we have to add heat as a reactant to that process. And so as heat is added, the equilibrium here shifts to the right to use up that heat. And this causes the concentration of the hydroxide ions and the hydronium ions to increase at the same rate. And so the pH and the pOH are lower because the hydroxide ion concentration and the hydronium ion concentrations are higher. Okay guys, so the first example here we're going to look at calculating pH for a strong base solution. And so the problem says find the pH of a 3.5 molar sodium hydroxide solution at 25 degrees Celsius. This is a strong base, so we assume it has complete dissociation, which means that because it's a 1-to-1 ratio in the compound here, we're going to get a 3.5 molar concentration of sodium ions, and we're going to get a 3.5 molar concentration of our hydroxide ions here as well. Okay, this makes this one a little bit easier. We're going to end up with a pOH value then. That's the negative log of the hydroxide ion concentration. And since the hydroxide ion concentration is simply 3.5 molar, we get the negative log of 3.5, which is negative 0.54. But again, it asks us to find the pH value, not the pOH value. And so then we're going to use our equation 3 from the previous slide here. We know that the pH plus the pOH is equal to 14, and so we've got the pH is equal to 14 minus a negative 0.54. Minus a negative is the same as adding, so we're going to end up with a pH value of 14.54. The last example here then is looking at our pKa and pKb values, and it says an acid was dissolved in water and the pKb value associated with its conjugate base was found to be 15.5 at 25 degrees Celsius. What is the pKa value for this acid? So we know the pKb value, and again, if we use our equation 2 now here, we know pKa plus pKb is going to be equal to 14. And so we've got 15.5 plus x is going to be equal to 14. And so pKa then, if we solve that equation, would end up being negative 1.5. Part B asks, is the solution acidic or basic? We know that it's acidic because the pKa value is less than the pKb value, at negative 1.5 for our pKa value versus the pKb value was 15.5, so we know that the solution is in fact acidic. And then, is the conjugate base a stronger or weaker base than water? Well, we know that this is a strong acid since we've got a pKa value that's less than 0. And so water is always a stronger base than the conjugate base of a strong acid. And so conjugate bases of strong acids really have no real ability to bond with hydrogen ions, right? Because again, those strong acids are going to go to completion and we're not really going to have any reverse reaction there. Okay guys, that ends the second video clip. In the next video clip, we will take a look at some examples of calculating pH for weak acid solutions and weak base solutions, and then in the final video clip, we'll look at those polyprotic acids.